So now that we know how to find the mean and the median in the calculator, we're going to practice with that again. What I would like you to do is put all the values in table 3 into L1. So we're going to go to Stat, Edit. You're going to go up to where L1 is highlighted in black, and then you're going to push Clear, Enter. I'm going to do that on both calculators. Stat, Edit, up, Clear, Enter. So let's put all the values from table 1, again in any order. Just push Enter between each entry. And there should be 12 total entries. Then we're going to go to Stat, Calc, 1var Stats, Stat, Calc, 1var Stats, down to Calculate. And the question is asking for the mean and the median. The mean is 7.25, and if we scroll down, the median is 3.5. So those are coming right from the calculator. And the question is, why are these so different? So why is the average over double the median? Usually the mean and the median are about the same. And these are the number of cell phone minutes from, I believe it's the author's daughter, on her phone. And so there was one time where she was on the phone for 48 minutes. And so that's because 48 is very large compared to the other values. And we'll talk about outliers later on in chapter 3, but 48 would be considered an outlier. It's extremely different from all the other numbers. So when you do have an extremely large or small outlier, it messes up the mean, because remember, we add all the numbers up and divide by the total to get the mean. It does not mess with the median. The median is in the middle regardless of high or low numbers. So that 48 seems like such a big deal, and it is for the mean, but it's not a big deal for the median, because the first number that would get ignored is 48 to get the median. So a numerical summary of data is said to be resistant. Sorry, I didn't give you quite enough space to write the word resistant if extreme values, very large or very small relative to the data, do not affect its value substantially. So the median is resistant because outliers do not affect it. The mean is not resistant. The mean is very sensitive to extreme high or low numbers. So I'm going to explain this a little bit more. Resistance is something that is important in statistics, kind of knowing what values affect what kind of numbers. So let's look at the top of page 3. So comparing the mean and the median with a set of data. If the shape of the distribution is skewed left, and that means the majority of the data is bigger and it skews to the left, that means that the mean is going to be substantially smaller than the median. If the data is symmetric, which means bell-shaped, then the mean is roughly equal to the median. They kind of fall right in the middle. And if the data set is skewed right, which means the majority of the data is smaller and you have a few extreme highs, the mean is substantially larger than the median. So to understand this relationship a little bit better, I like these 3 pictures, and these pictures are in your textbook as well. We have a skewed, that would be skewed left distribution. We have a symmetrical distribution, and we have a skewed right distribution. So if we have something that's skewed left, that means the majority of the data is here, and we have a low outlier. That would be like if everybody did pretty good on the test and one student didn't take it. So it would skew left because we have a 0 being averaged in. What happens is the mean becomes smaller than the median. It pulls towards that tail. So notice the mean, and we're looking at it on a number line where these are bigger numbers and these are smaller numbers. So the median is further up the number line and the mean is lower down the number line. So the mean gets pulled towards the tail and becomes less than the median. Here, the mean and the median are about the same. If we have symmetrical data and everything's pretty balanced, and you might have a few lows and a few highs, but they kind of balance each other out, the mean and the median will be roughly the same. If you have a skewed right distribution where the majority of the data is lower and there's one high outlier or large outlier, remember bigger numbers are here, smaller numbers are down here, then the median is smaller than the mean, so the mean is greater than the median. It pulls up towards the tail. So the mean gets pulled towards the tails, and the median stays roughly in the middle. So the median kind of stays where the majority of the data are. The mean is sensitive and gets pulled towards the tails. And I'm explaining the same concept a few different ways because I know it can be a little confusing. So the mean is what I call sensitive to the outliers. It gets pulled towards the tail or towards the outlier. The median is, we said, resistant. It will stay in the middle regardless of the outliers. So the outliers don't affect the median. So the mean and the median have kind of a unique relationship. Most of the time we report the mean because most data is roughly symmetrical or bell-shaped. Every now and then we're going to use the median instead of the mean if we have skewed data. I did mention in Chapter 2, this course does not focus on skewed data very much. We focus mainly on bell-shaped symmetrical data. So that's mean and median. Let's talk about mode. Mode is most often reported for categorical data. We don't study it very much in the course. It's usually for categorical data. Remember, the mode is the most frequently occurring value. And your calculator cannot give you the mode. You have to look at the list and see how many times does each number appear and is there one that appears more than once. And I don't have an example of mode. It's pretty easy. Let me go back and see. So let's look at the test scores again. If you want to go back to page 1, look at those test scores. I think every number only appeared once, but if there was like 2 grades of 88, that would be the mode. Or if there was 3 grades of 84, 84 would be the mode. It's whichever one shows up the most often on your list. So sometimes there's one mode, unimodal, when there's one number that occurs the most. Sometimes there's 2 modes where 2 numbers are tied. Maybe this one showed up 3 times and the other one showed up 3 times. So sometimes there's 2 modes. And sometimes there's no mode. So there's no value that occurred more than the others. Maybe all the numbers showed up once, or all the numbers showed up twice or 3 times. If they're all the same, there's no mode. So like in this example, there is no mode because each number was unique. There was no repeats. So again, we don't focus on mode too much, but that's how it works. So there's a nice summary in your textbook on page 118. I kind of just copied it right out of your book. Kind of summarizes the mean, how to calculate it, how to interpret it, and when to use it, the median, and the mode. Just a nice summary of 3.1. All right, let's move on to 3.2. 3.2 is some new material you might not have heard of before, but it's a very important concept. It goes with the mean. So we're going to talk about measures of dispersion. Dispersion is a fancy way of saying spread. How spread out are the data? And this is a very important measurement that we take in statistics because average does not always tell us enough. So an average test score of 75, if I told you the average test grade was 75, it could mean a lot of different things. And that's what I want to talk about, is why do we need to measure the spread? If I told you the average test score was 75, that could mean that everyone got a 75, right? That would give you an average of 75. It could mean that someone got 100. It could mean that someone got a 100. Someone got a 0, and everything in between. So it could be that the grades were everywhere, all over the place. It just happened to average to 75. It could mean that half the class got 100s. And it could mean that the other half got 50s. So if half the class got 100 and half the class got 50, that would also average to 75. So these are just different ways an average of 75 can happen. The last example I want to give you is that everyone got A's and B's, so 80s and 90s, but a few got 0s. So it could be that everybody did really good on the test, but a couple people didn't show up and got 0s, and that pulled the average down to 75. So this is where measures of dispersion are helpful. And we're going to call this spread instead of dispersion. Dispersion is kind of a weird word, but spread. How spread out were the data? Were they all the same? Were they all over the place? Were they split? Or were they skewed? And so we kind of need to get a sense of how our data is related to each other beyond just taking an average. So the first thing we're going to learn about is called range. That's the first measure of dispersion. Range is calculated by taking the highest data value and subtracting the lowest data value. We call the highest data value the max for maximum, and the lowest data value the min for minimum. It is reported as a single number. So if the highest test grade was 100 and the lowest was 60, the range would be 40. And I believe range is on your formula booklet. Always have this handy through these videos. So chapter 2 does not have much information on it. Fix the camera here. There we go. So chapter 2 just has the relative frequency calculation. The class midpoint's not something we need to worry about. Chapter 3 has a lot of information, and we're not going to look at all of this, but we are going to use a good deal of it. So population mean is on there, like we talked about in the last video. Sample mean is on there as well, like in the last video. We just talked about range, the largest minus the smallest. We are going to talk about standard deviation in just a minute, so we'll kind of keep referring back to this as we go along. There's a lot of good information on your formula sheet that you can use during the exams to help you remember some of this material. Alright, so that's range, pretty easy. Max minus min. The one we're going to talk about the most often that's going to stick with us throughout the course is standard deviation. We're going to hear this word over and over and over again, so it's the most commonly reported measure of dispersion. So standard deviation is kind of confusing. I'm going to explain it as best I can, but really you just need to know how to calculate it. So standard deviation is called the deviation about the mean. Deviation is kind of how far off from the mean are the different values. So what we're going to be looking at is how far each data point is from the mean. So if the average test score was 70, and I just keep using test scores because those are the most relatable for us. So these are just examples. You'll have different examples in your homework. If the average test score was 70 and you got an 85, your deviation would be positive 15. you are 15 points above average. If the test average was 70 and you got a 65, your deviation would be -5. And that would be 5 points below average. So deviations can be positive or negative, and each individual data value varies from the mean by either a positive or a negative deviation. If you did this for all your data values, if you subtracted each data point from the average and got a bunch of positive and negative deviations, if you added them all up, the sum would be 0. And I'm going to show you that in just a minute. But all the positive deviations balance out with all the negative deviations, and if you were to add them all up, the sum would be 0. Alright, so your textbook gets into how to calculate standard deviation by hand. I want to explain how to calculate standard deviation by hand, but I do not want to make you do it by hand. I'm going to show you how the calculator can do it for you. So you're more than welcome to learn how to do this by hand. You're more than welcome to do this by hand, but it's very tedious. The thing I do want to point out is a new Greek letter that we're going to look at. So you'll see this symbol down here. That little symbol is lowercase sigma. So we learned uppercase sigma is sum. This is lowercase sigma. It's a circle with a top on it. It's kind of like you were writing a capital letter T without picking up your pencil. And on your calculator it looks a little different. It kind of looks like a circle with a top, but it's a little more narrow than that. It's down and over. So that's called lowercase sigma, and that is the population standard deviation. So what you do to get this, and I'm just going to explain the formula real quick. You're not going to have to do this by hand, but if you take each x value and subtract the mean, like we were talking about with the test grades, you take that difference, you square the difference, and you add up all the differences. If we just added them all up, we'd get 0 every time. So in calculus, and this is not calculus based, but in calculus you learn to square your values so that the negative goes away. So we square all the deviations, we add them all up, so we have the sum of the deviations squared. We divide by the total to get kind of an average deviation, and then once all that's done, we square root it to undo the square. And I'm going to break that down for you here in just a minute. But that's what that formula is. So let's look at this for a minute. Again, I don't expect you to do this by hand, but I do want to show you how it's done. These are the same test scores from earlier. So you have your 10 students' test scores. You have your average, which we said was 79. They take the deviation or the difference from the mean, so they subtract, subtract, subtract. They get a bunch of positive and negative deviations, the difference between the score and the average. Some are positive, some are negative. If you added up all the positive and negative numbers, you would get 0. So the sum of the deviations is always 0. So that's why they square each one. So they take each deviation and square it. Squaring it gets rid of the negative. So these are all the squared deviations. This is the sum of the squared deviations, is this big number 964. So they take that big number 964, they divide by the total in this population, which was 10. So 964 divided by 10 is 96.4. The values are still squared, so the final step is to square root that number, and that gives you your standard deviation. So this is your population standard deviation. If you followed all of that, great. If that was a little confusing, that's okay. We're going to learn how to get that number in the calculator. It talks about sample standard deviation, which is the English letter S. And in your calculator, it adds a little X on the end. It's the same calculation, except you divide by what we call n minus 1, which we'll talk about later on in the course. I don't want to get into that now. So the formula is the same, it's just the sample size minus 1. And again, you don't need to know that because the calculator gives that to us as well, but it's the same process. Alright, so in the calculator, you use the same steps to find the means and the medians, which is called one var stats. Let me show you this real quick. We'll have to go back and put in the other values. The video might cut off, hopefully it will not. So if you put these values back into L1, and it's the same on either calculator. So stat calc 1 var stats. I'll show you on this one. You can kind of see the screen. The first thing you see is the sum of the x values, which we don't need. The sum of the x values squared, which we don't need. Let me move it over here in the light. You'll see SX, which is sample standard deviation, SX, that's the top number. And then you'll see the little sigma x, that's population standard deviation. So that 9.8 is right there. So the calculator doesn't know if you've entered population or sample, so you have to decide, was this a population or was this a sample? So that's the difference between those two. And you'll see that pointed out there. The sigma is for the population, the S is for the sample. Alright, I'm going to go ahead and stop there so the video does not cut me off. If you want to write this down again, 79 was our average, 9.8 was our standard deviation. Alright, I'm going to stop there.